Thanks you all for coming. My name is Juraj from IDEA StatiCA. This is Lubos, also from IDEA, and we got Graham from Arup, London. And we're happy to talk to you about steel connection design and about the workflow you use and how to improve it. We've prepared workflow examples, theoretical background behind it, and some explanation of how it all works. We will be switching us three the whole time. You can ask questions whenever you feel ready, or we can do that afterwards. We have time reserved at the end. We've prepared a handout. It's online for quite some time, and most important things there is a description of the two workflows with robot and advanced steel step by step. So feel free to use it after the event. Quickly, IDEA StatiCA, it's a solution associate of Autodesk. We develop software to work with Autodesk programs. I think I don't have to introduce Arup, and that's Graham's team, who are one of the most experienced engineers in the world. Today, together, we would like to introduce a different approach to steel connection design. How does it work? What are the theoretical principles, and how it is used in the practice, in the real world. And in the class summary, we used a word, any topology, and today we would like to hold to that word. That means to talk about standard joints, the one on the left. We all know that. The joints that are a little bit more complex, the middle one, but also the freakishly difficult ones. And it's not just about to model them, to draw them. It's about running full analysis and answer a simple question. Is it according to AISC or the Eurocode? Is it safe? Yes or not? And the objectives, learn about what is behind the software, the method, how to use it to design any joint pretty quickly. You will find out how it works with key Autodesk products. And this has been around for a while, so you will see it in project used in several countries around the world. Now let's start with why to even pay attention to this, why to spend 1 hour on steel connection design. Probably all of you have some CAE or finite element analysis program that can do analysis of the whole structure, and probably has a module or some kind of tool to deal with steel joints. And that is correct, and that is the right way to work. So we work with the whole model, but the thing is that in practice, majority of problems we get are related to details, to structural joints, that either through the building process, engineers spend time on figuring out the devilish details. And that leads either to waste of time of the engineer or waste of material when we want to be on the safe side, so we just put more materials there. So we're trying to come up with a solution focused on joints so that we can answer all the questions. And we got two groups of joints. The standard, right, well described in design guides, and the non-standards, the difficult ones. And to deal with standard, right, we just need to take a look in the design guides, follow the procedures that were well followed before, and get the job done. With the non-standard joints, it's a different story. We have to use advanced scientific models, a lot of Excel spreadsheets, sometimes estimate a little bit, and honestly, sometimes it's just better to avoid it and change the project a little bit so we can use the standard joints anyway. I think you all remember when you were studying your college degree, you had to pass, I think, 40, 50 exams during the whole time, and not all of them were the same in terms of toughness. and you probably spend most of the time on the 10 to 15 most complex exams. And steel joint design is very similar. We spend majority of our time on the lower amount of joints. These are the non-standard, the difficult ones. That shows us that we are okay if we seek an option, to do the steel connection design better. And the new approach we will now explain. We'll start with the theory. Luboš will guide us through the method, what are the assumptions, and how it works.
Okay. When we design steel joint, we normally have internal forces calculated from the 3D model, from 3D frame, and usually when we want to analyze the joint and connections of members, we use component method, which is implemented in design codes. And this method is based on a simplified model where the whole joint is divided into small components. Each component is modeled by a specific spring, and we calculate the forces in all parts of connections on this model of these springs. It's a normal approach, which is quite common, and it is very good and safe method and widely used. The only problem is that this method is not general enough. In fact, for each shape of or each topology of the joint, we have to derive this specific model of these springs, and this is a problem because not everybody is able to do it. So we came with the idea that if there is the problem with making models, we do it with finite elements. Finite elements is used for analysis of the whole buildings, whole structures. So why not to use it for steel joints as well? In the component method, when we calculate the forces in bolts and welds, we apply specific checks according to code, and with this new approach it is the same. We calculate forces with finite elements and then apply the same checks for bolts, welds, and other parts of connection. It seems to be very easy, but if we want to get it, we have to apply some quite specific things. The first one is that steel is plastic material, and so we have to implement or we have to calculate elastoplastic models. You can see the strain diagram for steel, for real, which you get from tests. But in our method, because we want to make checks according to code, we use the diagram which is according to code. It is this green one, this simplified elastic plastic diagram. And when we use it, we cannot do the checks for the stress, but we have to check the strain. And it is recommended according to codes that 5% of equivalent strain is a value which cannot be exceeded. In the new CB FEM method, we implement several new features, things. One is regarding to finite element solver and meshing. It is the fact that most of CAE programs were were invented in 80s, 90s of last century, and from that time there is not a big progress in these models. But in other industries, yes, for instance, in aircraft industry, they do not use, when they want to connect to plates, they do not use intersections of these plates, but they connect these plates by so-called interpolation constraints. And we do the same. We mesh each plate separately, then the mesh is very simple, and there is not big amount of elements, and we connect these plates with these interpolation constraints. And if we do it, we have directly forces which we can use for design of welds. We model also bolts with specific models, and we use quite simple strings, but also these strings has nonlinear stress force deformation diagram. Little bit more complex model is applied for analysis of shear in connection. But you can see on these examples that we are able to calculate the real situation in the plate when the bolt press only one part of the hole, and the other part is not loaded at all. On these pictures you can see the plate on the top flange of the beam connection on bottom flange, and you can see that all plates are loaded in opposite direction. Welds are very important part of steel connections. We applied elastic models which are based on these interpolation constraints, and we just calculate forces in these constraints, and then we take stresses and forces in welds and apply checks according to code. But recently we came with a more advanced model where we calculate really with full plastic model of welds, and this approach bring more safe and more realistic design of welds. In our CB FEM method, it's possible also implement contacts between plates. We have contact elements where these contact elements work only in pressure, not in tension. In tension, the joint is or the connection is opened. And thanks to this, we can calculate also such examples of connections. Of course, we model also base plates and anchoring. The concrete block is calculated like subsoil. In fact, in the same way like you calculate buildings on subsoil, we put the model of joint on this subsoil with concrete characteristics. And we can evaluate the contact stress between plate and concrete, and calculate average stress from it, and check it according to code. This method is not very difficult from a theoretical point of view, but it's quite new, and we knew from the first moment when we start this development, then we have to convince you engineers. So we pass a lot of verification and validation examples. At first, we compare the simple connections where the design is known from books and guides, and we compare the simple examples. Then we do a lot of examples with advanced models. Maybe you saw this in some artificial articles or on university outputs. And we also calculate these models and compare it with our CB FEM method. And we cooperate with two technical universities, and we pass also the real life testing in labs. And a result of this verification was this book. We have this here. We do something at the end of the lecture with this book, and all these verification examples are inside this. So it was about theory behind of this solution, but maybe it is not so important for daily practice. For daily practice is that the product has to be incorporated in your workflow, and so we connect this software with most of Autodesk structural software. At first with Robot. In this, there is the possibility that you calculate the structure in Robot, then select the node, and from this node this is exported to our software, and we can make a check of the joint. It is you can see it on this example. This is structure in Robot. You can select the node in plugin menu. You select our function, define the name of the file. Then the data are sent to wizard, where you can see if the node is really the same as in the Robot. You can make some small improvements or changes. Then you go to StatiCA program, where you see the real shape of the node, and we import all internal forces from Robot. These forces are applied on the model, and then the node is designed. We cannot use standard templates like in advanced steel because our nodes are quite complex or can be complex. So the whole approach is based on we call it manufacturing operations, which are in fact the same how the node is built in reality. So there are cuts, there are end plates, there are cleats, fin plates, and this, and you can combine all of them in one joint. So you see the needed model of the joint, and when we have it, then we apply the new CB FEM method, which is quite complex, but you do not care about finite elements, everything is done in background. The model is done automatically. It is important to say that you as engineer, you don't work with finite elements. All this meshing and the model is composed in background, and you only get the results in the standard way, like in finite elements programs. But also we prepare some special special presentations, like here you can see the plastic parts of the joint. You see the critical places in this joint. And of course, finally, we generate a report with all input and all results. It's not the end of our class, it's the end of this video. The method is used more than 2 years, 2.5 years, and during that time we came across a lot of interesting projects and also things which were not designed very well, and we find the problems. With this method, we can make the analysis of stress and strain in the joint. We can do also buckling analysis, so the local buckling in the joint can be analyzed. We can analyze the stiffness of connection of any member to the joint, and we can present the results in a very simple and understandable way. We have several real-life examples. For instance, with this this is the project from Poland, where engineers designed in not very good way the connection of this diagonal member, and it led to real plastification of this node and in fact to the collapse. And we little bit rearranged the nodes, changed the shape of the plate, and you can see on this that finally this design is very nice and safe. Another example, it's about stability. Such a joint was designed. You can see this this way how we present the results. We call it traffic lights presentation. You see where the design is satisfactory and quite optimal. And all these items are green. The parts which are close to the limit, they are orange. If there is something really wrong, it is red. Yeah? So you can see that from the point of view stress and strain, the joint is designed correctly. But when we do analysis of buckling, there is a little bit another situation, but you can add stiffener and directly see that this problem is fixed. This example is about stiffness of the joint. Again, it is the crossing of diagonals of bracing, and it was done in this way. And when we calculate it, you can see that it is designed properly from the point of view stress and strain, but not from the point of view of stiffness of the connection. And there is ovalization of this tube, and it's not very good for this connection. If you do it in this different way, then you get the joint which is 10 times stiffer, and in fact for the same money. This is an example from Heathrow Airport in London. Our method was applied on the bridge in extension of the airport last year, and there were connections which were not possible to design it according to basic simple component method guides, and we applied this CB FEM method, and we are able to design this bridge. And now we have part about using of CB FEM in Europe, and Graham will continue.
Thank you. So this is a flavour of some of the work that we've done in Arup in London, just to give you a feel for what we are using it for as a designer. So these are a range of project types that we have, all of them being steel apart from the Sydney Opera House, but I had to get that one in. So all these are steel structures that have exposed visible connections predominantly, and so we have to have a way of being able to design these in as quick and as simple a way possible. So what we were after was a tool that was allowing an efficient workflow, so that involves interoperability with all the other tools that we use, be it advanced steel or Tekla structures. I have to say that once. Be simple and easy to learn, and fully supported by codes and validated. And you've heard already some of that validation that's gone into this tool. There's a tremendous amount of effort that's gone on by the guys that have got this tool together. And also, we want a tool that's used from the early stages of projects to help with feasibility and buildability studies, all the way through to detailed design studies. So I'm going to show you a few more examples in a second. To us, from the UK, it's a tool that uses Eurocode, but it also uses the American AISC, so that you've got the ability to use it to either code. But in particular, in the Eurocodes, there's the parts 5 and 6 of Eurocode 1993. So that's Appendix C in that, or more correctly, Annex C, deals with plated elements. And there's also part 6 to the Eurocode 3, which is about shell structures. And so the tool uses both of those. And I would suggest it's well worth a read, particularly the bit in the part 5 here, which is about needing to understand how finite elements work in your design tools. So it's a good read. It's not a particularly long read, but it helps understand what the tool is trying to do. So that's one thing I'd recommend. So some examples of its use. Now, 10 years ago, this is the Leadenhall Tower in the City of London. And the nodes that we were analysing and creating there, that's one particular node that's about 3 meters from top to bottom, channeling huge amount of force through the plated elements. So we had to go through that in quite a complex way 10 years ago, which involved Nastran analysis and LS-Dyna stress plots to work out welds. So we still use a lot of this methodology, but what we've got out of this tool is a much quicker, simpler way to analyze the likes of a node like that. We were also being able to create weld plots, looking at different load cases. But this tool, the StatiCA connection tool, is able to produce all of this in one output and very quickly as well. So now, this is an example where on the bottom left is the stress plots from the tools that we would normally have used, which is LS-Dyna. And that's looking at a particular tubular structure with a strut. So you can see that in the top of the image. There's a strut coming down there, fixing up to a tube. And so the reason this came to us was because the connection was unstiffened, and we had to look at how this connection, taking all the loads into an unstiffened box, was going to behave. And we found quite good correlation in how we were doing it before to the tool that we used in this. And in fact, the inputs are slightly different in the two analyses, so it's not a direct comparison, unfortunately, but nevertheless, we were pleased to use this. And we were also looking at 270 load combinations in one go. Part of the problem of enveloping results, as engineers, you probably grapple with this all the time. You have to either envelope all the results and provide one set of forces, or you look at all the possible load combinations, including pattern loading. So here, the tool is able to go through each and every one of those load cases very quickly, and so we use that to help home in on which were the most appropriate load cases to consider in more detail. And here's another example. This was a bit more forensic analysis. We were called to a contractor's site where they were seeing the ends of a truss cord, which is to the right of this image, which was a cantilever. They were seeing that cantilever deflect quite a lot. And all the force in the tension in the top cord, which is shown up on the right here, was being channeled down the brace behind it. And from the visual site inspection, we were able to see that this connection was probably one of the reasons the contractor was observing quite large deflections in the cantilever. So we looked at this in the tool, and from the geometry that we knew, we were able to apply the various manufacturing operations as described already, and develop a very simple connection. And this is, when you're familiar with the tool, it takes about 20 minutes to do this, or maybe even less, in fact. But then you can analyze it and interrogate the results, which is the important bit. And so this was the stress results, and as you can see on the left, all the plates have a tick here, so that statically this connection was doing all it was being asked to do, to channel the forces. The problem came when you look at the deflected output from this connection. So if you remember, there was a tension force in this top cord, which was having to be resisted by the brace. So all the plates were being pulled apart, and it wasn't a very stiff connection. And you can see that by the way that the connection was opening up. And you can see particularly top right, there is an end plate on this connection here, which is a tube, and that end plate was bolted below. Also, this was a PFC, a channel section, with the bottom web part being pulled down by the gusset attached to the brace. More obvious as you toggle through it. So the StatiCA also has the ability to look at the stiffness of a connection. So that is the stiffness plot, clearly showing the weak links. So there's the end plate on the right and then a part of the end plate on the top. This was not a very stiff connection, which was it was very obvious to us on site because it was what we went to have a look at, or my colleague. But the tool could have been used, or should have been used, much earlier in the project by the person that did that connection, and that would have immediately shown the logic of what was wrong with that particular connection. So another couple of examples. This was a plate where hidden inside of it were lots of stiffeners, and we were looking to see whether the stiffeners could have been removed or reduced in size, and we were able to conclude that the stiffeners were about double the thickness that was needed, so we halved those, which worked well. So a few more examples just to wrap up. Tubular structures with bolts, so we've been using it to look at those for welded connections as well as bolted connections. We're using it with advanced steel to link to a roof cord, as you can see here. So on the left is advanced steel, and on the right is the output into StatiCA, which this is a hot off the press, so this is being analysed at the moment. And then a couple of other examples of the sorts of things we produce, where these connections, this one and this one as well, we as engineers have to know that what we're providing is fully buildable and designable. There's no point in offering up a connection to a contractor to design if that isn't the case. In many of the examples I've shown, we are, as an engineer, responsible for those connections as well. So the workload spreads the whole gamut of us being, as engineers, responsible, or the contractor being responsible. But ultimately, we have to know that it's buildable. So the tool allows us to take the output from, say, an advanced steel model and very quickly run through those options. So those are my examples. I'm going to hand back now to talk a bit more about advanced steel.
Thank you very much. Thank you very much, Graham. You mentioned advanced steel, so we're going to jump into this workflow. We'll follow the same logic. We'll select a node in advanced steel. It's a different game. In advanced steel, it's a highly advanced modeling software, so we will have all the manufacturing operations done, but we will need to input the loads so we get the full set of load cases we need for that particular example, so we can get to the check. We implemented in a way that the workflow is started with a command. It's called concheck after it is integrated. So I run a command, concheck, and then I select the node, then the members, and then all the joint as a whole. That means including all the bolts, welds, and once I do that, it automatically ships all these data to IDEA StatiCA connection, creates a new project, imports all of it. So we basically have zero work in the geometry and the design compared to if we start from scratch. And we can go directly to load effects. Here, we usually look for load effects put together in other FAE program. Here we used a simplified input from the Excel spreadsheet, so we get the load cases there, and we can go to the check itself. So run the analysis, and this can be, as Graham pointed out, in any phase of the design, the concept, or the finalization. So I get the results. It checks for all plates, bolts, welds, what is okay, what is not, and we can visualize the results in a different way to get the necessary information. So this is more close to the fabricator's workflow, and during the whole process, I will do that several times, we know where we are in terms of how the joint is loaded. Here, I will launch it again. We are gradually loading the joint, and you can see the plastification zones develop. And we wanted to make it pretty easy, so green is okay. Once we go to red, that's where the joint fails, and the design has to be changed. We also give option to not just be on the safe side and save time of the engineer, it's also about the material optimization. We've prepared one example how we can study the forces in bolts and come up with a better design. Luboš?
So we can show the possibility of optimization of bolts on this example. This quite typical example, which is recommended example of connection, which is recommended for seismic regions, and it is quite stiff connection, non-dissipative from the point of view of seismic design. There are two rows up the flange and two rows below the flange. And when we calculate it, we have internal forces or not internal forces in all bolts, and with our traffic lights presentation, you see which bolts are designed quite okay. They are green, but there are also gray ones which are probably not loaded so much. On this example, on this picture, you can see the forces in bolts, and the bolts in corners, they do not take almost no force. This is a little bit can be surprising, but this is a real situation. If the plate is not stiff enough, then the distribution of forces is really different than for completely stiff plates. Okay, so in this example we have 32 bolts, but maybe we can do something with them. And in our tool we are able to edit the position of bolts and maybe delete some of them. So in the first step of optimization, we deleted 4 bolts in the corners and calculated again. And you can see that, in fact, nothing has happened. These bolts in corners were really not used. So we can continue in optimization, and we tried to get rid of also the bolts in the second row below the flange. And again, now we have only 20 bolts, and the design is still satisfactory. Only you see the forces in bolts that now almost all bolts are loaded with the same force. Yeah? But we can continue and try more, and we deleted also bolts in this row below the flange, and let there only one in each side. And now you can see that this traffic lights presentation, that the red color appeared, and these bolts are red, several welds are red, and also the stiffener is plastified too much. So it is this optimization is too much, and we have to use the previous design, which is this one. And in our CBFEM method, we can calculate any topology of bolts. It's not only the typical number of rows and these lines. Yeah. Okay, so this is the situation when the connection is not satisfactorily designed. And now we can continue with another workflow with Autodesk software, which is Revit. It's a quite new development, which is not completely finished, but we can show also this. There is the structure in the Revit. In the Revit, the difference from other FEA software is that in Revit there is the object called connections. You can define connection directly in Revit. Define, it means the node and all connected members. And then if it is done in Revit, you just click on this connection, and it is important to idea StatiCA. With all load cases, combinations, which can be in Revit, and so all these things are imported. Maybe some combinations can be edited or modified, and then it is the same as like in robot case, that we have this joint in our tool, and we can add these manufacturing operations. Here are all loads, and then with manufacturing operations we can design all joined. Here you can see also these dog bones details, which are obvious for seismic regions. And again, we calculate it and see in this traffic lights presentation, some bolts are on the limit, but the design is done very well. You can see the places of plastification. and again we can generate the output report. In the report, all welds or bolts are checked, each plate is checked, and some simple drawings are provided. Okay.
Very well. So you've seen what is it working on already. You see the closest future update. That's the Revit in April, and we're also working on the Forge interoperability. Forge is the Autodesk platform, the cloud platform for cooperation. This is the preview from 2 weeks ago when we took part in the Forge Accelerator in Munich, Germany, and the first joint sent to the Fusion API of the Forge, which is a pilot project to link this technology with cloud models of Revit, etc. So we will gradually do more things with this. The easy thing is to leverage on a drawing engine of Autodesk products, because that's just 100% great. So even though we can generate our own drawings, it's much better to use the cloud API to generate precise drawings in DVG. And further down the horizon, when the Revit cloud model is being rolled out or will be rolled out to Forge API, we can link to the cloud Revit model, take any joint from Revit, design it, check it, send it back. So hopefully you will see that in the next year's catalog of classes for AU. Before we go to Q&A, we've got two more things. Please give us feedback. And at the beginning, Luboš mentioned that we have one book, and this book is for one of you. Let's do a little bit of competition. We would like to ask you one question. It will be on the next slide. When you feel confident that you are ready to answer it, please raise your hand. And the first one to get it right will receive this book from us. Okay? So everybody ready? Let's do that. So, how would you compare steel joint design using component method and the CB FEM method? What is different? What is the same? So we'll see who will be the first one. Yes, please go ahead. Excuse me? Okay. All right, outputs are the same. And how do we put together the model? What is the difference between the component and the CB FEM? All right. And in terms of the tools it uses to build the model, what's the difference between the component method and the CB FEM? Graham also mentioned it, that it's important to know it as a background, what is behind it. Exactly. That's the difference, putting the model, and then we get the same checks at the end. Very well. So let's give it a heads up. Congratulations.
Thanks.
All right. Let's do questions. We have 10 minutes, so feel free to ask, guys. Okay, so the question was if in the output report we can display all the equations used behind it and the references to the code. Yes, the output is scalable, and we provide references to the specific parts of the code and the equations used. It's slightly different to the component method as there are finite elements involved, but you can get into the core of it and see what it did.
It also does the detailing checks as well if you ask it to, so it can look at bolt spacing, etc.
Please.
Would you use the same method for when you demolish the buildings to figure out when a removed part of the buildings, what's going to happen?
That's interesting. That's the question is if we use it while putting the structure down, not when building it. I'm not sure if one of our users have tried that. But the analysis of the building of the structure is both ways, but I'm not aware of an example that somebody used that in this way. Bosch?
In fact, we use internal forces which are calculated in the 3D model of the structure. So if you calculate the demolition of your frame, then you can use these internal forces in our tool. Yeah. So in fact, it is design tool. It's not analysis of the structure, but it is standard design of one joint.
Please.
Will your design tool work with what I call a pre-engineered building made from a welded tapered beam, so it's made out of plate sections rather than a standard section, and you put a connection on the end? Will it still design the connection in contrast to the actual beam not being hot formed? It's made out of plates welded together. It's quite a common construction in the North American market, so for beam building design. It's pre-engineered building market.
All right. Do we get that? Graham?
The tool does allow you to select different section types, cold formed, hot rolled, so you could select the standard sections or you could create your own plated sections and you just tell it to the plate thicknesses, depths, etc. So you can build up your own sections in it, if that's what you're referring to.
Yeah, so like in the North American market, they basically have tools, we don't do any use hot roll sections, they bespokely design the building using a welded tapered beam arrangement, where the section depth changes and alters throughout the design of the building, and then you need to basically reconstruct it. But you put a standard connection on the end of it like an end plate, but the horn is replaced by a beam that's tapered out. It's going to design the end plate. Yeah, I think it does. You said you could design it.
Yes. And you can apply manufacturing operations as well. So to a standard incoming section or a plated I-beam, for example, you can define cuts in it or holes or add plates as well. So you can build up a section in any number of ways. It's very versatile.
Thank you. All right. If you want more information on this, just please exchange a card with me, and we'll send you the full information. Or visit our website, idea-rs.com. Drop me an email. We'll be around for another 10 or something minutes, so if you want to talk to us, no problem. Thank you again for attention. Hope you enjoyed it.